let's do matrix operations on a vector. You could imagine this could be anything like a rotation matrix or something like that. It doesn't really matter. We're going to talk about this from a mathematical perspective. So I'm doing a two-dimensional vector matrix operation, and we're going to do the eigenvalue problem. So there's a bunch of work we're going to do, and we're going to do a bunch of different ways, 3 different ways. Okay, and we're dealing with just 2 dimensions because it gets complicated more dimensions you add. So suppose I have the operator that looks like this matrix, 5, -2, -2, 2, and I want to operate it on this vector R1. What would that do? Well, we can do that operation. I can do AR, I'm just calling it R. AR is going to be this matrix, 5, -2, -2, 2, operated on the vector 1, 1. So to do this calculation, I'm going to take this vector and essentially dot it into that vector, treat that as a vector. So that's going to be my first element. It would technically be a row vector. I always write them always as columns because I don't care. But here I'm going to get 5 times 1 plus -2 times 1. And that's going to be equal to 5 minus 2 or 3. Now I do the same thing over here. I get -2 times 1 plus 2 times 1 is 0. So there I did it. And that's not the eigenvalue problem. This is practice warm-up. Now the question is, are there any vectors that I could take and operate A on and get the same direction? So this is the eigenvalue problem. AR is lambda R. So it means I operate A on the vector R and I get some constant, some scalar constant times that same vector, same direction. So think about, in terms of rotation, what vector could I have such that the rotation vector wouldn't do anything? That's not the rotation matrix, okay? That's just a generic matrix. What I want to do is to do this in Python. And I'm going to do it in VPython. Later we'll use real Python. But I want to do it in Python so that we can see what this looks like for different vectors. I'm going to take the same matrix and I'm going to operate on different vectors and see if we can just kind of play around and find a vector that's in the same direction. Because that would kind of give us a mental picture of what's going on. I think that'd be awesome. Now, let me go ahead and say that VPython does not have a matrix operations built in, and it does have vectors. So I'm going to cheat, right? I'm going to say, next, I have to say that we have 3-dimensional vectors in Python, in VPython, not 2-dimensional, but that we can take care of in a second. So I'm actually going to say A is, I'm going to represent it as the vector AX, AY. So AX is the vector, I'll use my normal vector notation. It's going to be that vector, 5, -2, angle brackets. And AY is the vector, -2, 2. So when I do that, if I take this and operate it on that vector, I'm actually going to get the dot product right there, which I have. Now, my matrix is actually going to look like this in Python. It's going to be AX vector, AY vector, AZ vector, because it has to be 3-dimensional vectors. And so AZ is actually going to be the vector 0, 0, 0. But what I want to do is to make a function that takes a matrix, a 2x2 matrix, but actually works for any matrix, operates on my 2x2, my 2x1 vector, and returns the vector. And then we can draw those as arrows, and then we can play around with it. So let's just jump into VPython and do this. And I really think this kind of helps us understand what's going on. So I have VPython right here. Let's just go ahead and define our function. I'm going to call this vmult. I'm going to call this a def vmult. So vmult takes the matrix, let's call it AT, and the vector VT, and it operates them together. So I'm not going to put comments in there because I'm just trying to get things done. So what I'm going to do is to first represent my vector. I want to give vectors or matrices as a list of vectors. So AT is a list. So I need to turn those back into actual vectors. I can calculate the components of my resultant. I'm going to call it CX, CY, CZ. So CX is going to be the dot product of the first component of A list, which is going to be AT0. That's a 0. And VT, right? So that's what we did up here. We took the AX dot into V, and that was our first component. That's CX. And then CY is going to be the dot product of AT1. The second item in my list of A is my second vector. And that's going to be VT. And then CY is going to be equal CZ, dot product of AT2 with VT. Now I'm going to return the vector CX, CY, CZ. That's my function. Okay, let's see if it works. So I'm going to make my matrix right here. I'm going to do the exact same thing I just did up there. So A is going to be equal to the list of, I'm going to call that vector 5, -2, 0. Right? I have to have that Z component. I can't make a two-dimensional vector. And my next vector is going to be equal to vector -2, 2, 0. And then my last vector is 0, 0, 0, because I have to have that. And then we did, which one did I do? I did 1, 1. So now let's say R is the vector 1, 1, 0. And let's just print. I'm going to print A. I don't want to show you what that looks like. Print A. So there's my A matrix, right? It doesn't look like a matrix, but if you put this down there and you put this down there, it's a 3 by 3, and then all those zeros are going to make it just a 2 by 2. Okay, so now let's just print. I'm going to call this R2. R2 is vmult AR, and let's print that. Three, 0, 0. That's what we had before. So it works. So that's good. Now I'm going to draw two arrows. I'm going to draw an arrow for R and then R2. What did I call it? R2? Yeah. So I have those two arrows. So I can look at the vector I start with and the vector I end up with. So let's call this R arrow. It's an arrow. Its position is vector 0, 0. I'm going to start them both at the origin. Its axis is going to be the vector R. And then I need a color. Color equals color dot yellow. And let's make the other one R2 arrow. And it's also an arrow. It's a three-dimensional object. Positions also at the vector 0, 0, 0. And the axis is going to be equal to R2, which I have now. And let's make this one cyan. Color equals color dot cyan. And so let's just run this and see what happens. So there's my vector I started with, right? There's R1, the initial R1, 0, 0, and that's my new one. Now, I do want to do, I'm going to adjust the shaft width of these arrows. So you have this normal arrow right here, and as it gets bigger, it makes it wider, and I want them all the same length just so we can see them better. So you don't have to do this, but I'm going to put, oh, you can't even see that. Let's put it up here. So, can you see that now? Yeah. So let's just wrap this around. I'm going to put a comma there, and there's a property called shaft width, and I think 0.04 might be a good value. Let's put it on this one too. Shaft width. They're the same width. 0.04. I think that, I can't remember how it's defined, but I think that should work. Let's run it again. Oh, that doesn't look right. I must have misspelled shaft width. Aha, I did misspell that wrong. And let's make it bigger. Oops. 7. I don't know why I'm picking 7, but I'm picking 7. Okay, so there's my two arrows, and they're, starting arrow, final arrow. Now, we could just manually pick different vectors and see if they end up in the same direction, and that would be fun, but I'm not going to do that. Instead, what I'm going to do, just because I want to do it, I'm going to rotate my vector, my cyan vector R. I'm going to rotate it around through the whole space, and we can just see what happens. So let's do that. So I'm going to say theta is equal to 0, d theta is equal to 0.01, and then while theta is less than 2 times pi, rate, let's put rate at 100. I'm not good with rate. 100 might be too slow, but I think that's fine. what I'm going to do is to calculate my r vector based on that angle theta, which I misspelled. Right. So let's say r equals vector. It has a length of 1. We're just going to keep a length of 1. It's going to be cosine theta, sine theta, 0. Right? So now it's just going to rotate around, and then I can increase my value of theta. So theta equals theta plus d theta. But now what I want to do up here is also calculate R2. So R2 is going to be V molt AR. Now I need to change the arrows, right? So I'm going to change both of those. So let's change that. I don't need to change the position. R arrow dot axis equals R. R2 arrow dot axis equals R2. Let's just see what kind of damage we did here. I don't even know if it's going to work. I think it should work. There. 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 So you can see at some points as we rotate this thing around, we get vectors in the same direction, and those are the eigenvectors. Those are the values that we want to find that show the vector and the operated vector is the same direction. Let's find that analytically, and then we'll come back and test it here, and then we'll do it in real Python. That's the goal. So let's switch back over here, and let's find those values of R, the vector values of R that work here. I'm going to move this. So I have A, 5, -2, -2, 2. That's the vector we're going to deal with. And we want to say AR equals lambda R. So that's a scalar, and that's a matrix. Well, one thing I can do is to take this side and operate it with the identity matrix. So 1 lambda R. So the identity matrix is 1, 0, 0, 1. Is that it? Okay. And so if I do that, I don't change that value, but I make this a 2 by 2 matrix on the right-hand side, and I have a 2 by 2 on the left-hand side. So now what I can do is I can subtract that from both sides, and I get AR minus 1 lambda R equals 0, and that's the 0 matrix, 0, 0, 0, 0. Now I can actually factor out the R. So I can write this as A 1 minus 1 identity matrix lambda operated on R is 0. So how is that function going to work? Well, either R is 0. And if I put in a 0 vector, I should get a 0 vector back. So that is technically an eigenvalue, although boring. We don't want to do that. So the other way is that this is essentially 0. So one of the ways that would be 0 is if the determinant of this is 0. So I want to say the determinant of A minus 1 lambda is equal to 0. So that's the determinant of the following. I'm going to say the determinant of 1 minus this is going to be this minus lambda, that minus 0, that minus 0, that minus lambda. So I get 5 minus lambda minus 2 minus 2, that's a lambda. 2 minus lambda is equal to 0. That's what we want. We want that to be 0. Well, we can take the determinant of a 2 by 2 matrix. It's not too hard. And we get the following equation. I get, I'm going to put over here. I get this times this minus this times this. So I want to put it right here in the middle. I'm just going to erase that. So I get 5 minus lambda times 2 minus lambda plus 4 equals 0, right? Because, no, wait, that's going to be 2 times negative 2 times negative 2 is 4, but it's minus. I'm sorry, it's minus. So that's what I want. Now I want to solve that equation for lambda. Okay, so here let's just multiply this out. I'm going to get 5 times 2 is 10. I'm going to get negative 2 times plus negative 5, so it's negative 7 lambda, plus lambda squared minus 4 equals 0. Let's just rewrite that as lambda squared minus 7 lambda, and then I have 10 minus 4 plus 6 equals 0. Now, how do I find values for that? You know, if you're lucky or if you can think really well, you could factor this. And if not, use a quadratic equation. That's what the quadratic equation does. It factors this. But I think here we could say this is going to be equal to, if I have what plus what is 6, and no, what times what is 6, and what minus is, or added together is negative 7. So if I have negative 1, negative 6, so if I have negative 1 times lambda minus 6, that works, right? Because I get 6, and then when I add those two together, it's 7. So I did it. And so this would have two solutions for lambda. I have lambda 1. This term has to be 0, so lambda 1 is 1. And then I have lambda 2 is, this term is 0, so lambda 2 is 6. So those are my eigenvalues. Now, how do we find the eigenvectors? So let's put that up here. Lambda 1 is 1. Lambda 2 is 6. I dropped my eraser. Okay. If I assume lambda 1, then I can write the following equation. 5, negative 2, negative 2, 2, operated on some vector x, y, I don't know what that is going to be lambda 1, which is just 1, x, y. Now, if I do this operation, if I take this on that, I get 5x minus 2y equals 1x, right? Because this operated on that gives me this times that, which is x. And then if I do the second one, which I kind of scrubbed those out, I get negative 2x plus 2y equals y, 1 times y. So you think, oh, I have two equations. I have two unknowns, x and y. I can solve for x and y. You can't, okay, but that's fine. So let's just take this right here. I'm going to add 2y to both sides and subtract that. I get 4x equals 2y, or x, or 2x equals y. Now, if I plug that in up here, let's just do it. I want to show you that it doesn't work. Let's take this and plug it in up here. I get negative 2x is going to be negative y. So this becomes negative y plus 2y equals y. So I get y equals y, or 1 equals 1. See, so it doesn't really tell me anything great there. So I don't really get an extra thing from that. So this doesn't tell me the whole solution. But it does tell me the relationship between x and y. Any x and y that satisfies this will work. So if I say y equals 1, x equals 1, y equals 2, that works. If I put in x equals 1, y is 2, that works. So the vector 1, 2 should be an eigenvector. Okay? That means that should, if I operate this up here, I should get the same thing. So if I replace this with 1, 2, then what do I get? I get the vector 1 times 5 minus 4 is 1. And I get negative 2 plus 4 is going to be 2. I actually get the right thing. It worked. And I have the right eigenvalue of 1. Okay, now to find the next eigenvector and value, I would just use this lambda. I'm not going to do that. Okay. But the other thing that I should point out, that normally we would write this. This doesn't really matter. I can multiply it by any number. If I use 2, 4, it would still work. If I put in 2, 4, 2, 4, it would work. So what we would do is to normalize this. So if I say r is the vector 1, 2, then we would write r hat as the vector 1, 2 divided by the magnitude of that, which is going to be the square root of 5. So that's what you would do. Okay. Normally we would put it in as normalized. Let's just check if this is indeed an eigenvector with our Python, and then I'm going to solve for the other eigenvector with real Python. Okay, so going back to the computer right here, let's get rid of our loop. I don't want to loop over the thing. Let's do this. 1, 2, 3. 1, 2, 3. So that comments that stuff out. Now I'm going to just say R1 up here is, what did I say, 1, 2. And let's print R1 and let's print, I did print R2. That's fine. Okay, so there, you can't see the other vector because they're right on top of each other, and there's that other vector, 1, 2. It did indeed work, so that's kind of awesome. Okay, now let's solve for this with real Python. And I want to do this in real Python because 2 by 2 is not terrible. You can do a 2 by 2. 3 by 3 gets a little, I don't want to do that. I don't want to do a 3 by 3 eigenvalue problem because it gets really bad. And spoiler alert, we can do 100 by 100 eigenvalue problem matrices, and we will do that in quantum mechanics or to solve different boundary value problems. So that's kind of cool. So let's switch over here to real Python. I'm using Jupyter Notebooks. You can use Google Colab. Either way, it's fine. But the number one thing that we need to do is to import the one module that we need to use, and that's NumPy. Some people call it NumPy. You call it what you want. So import NumPy as NP. So this says that whenever I use NP dot anything, it's going to get it from that module. Really important because you could be using more than one module, so you need to do that, and you need to have a name for each one. Okay, the first thing I'm going to do is to define my matrix. I'm going to define the matrix A as an array, a NumPy array. So A equals NP.array, and then I need to give, so it looks like a list of lists, but it's really an array is something different. You can do different things with it, so you have to have it as an array. So, but I'm just going to enter my number here, which was 5, -2, and then the next row was comma, another list, -2, 2. And let's just print that just to make sure it works, right? Print A, run that cell, and it did not work because I didn't put that as a list. I forgot that other bracket right there. I do that all the time. There's my my matrix. Now what we can do is very simple. Okay, there is a eigenvalue function in NumPy that just says, okay, you give me a matrix, I'm going to give you the eigenvectors and values. So we can call that, I'm going to call this AW. So I'm not sure why, but I always use, it was because of another problem. So A is going to give me my eigenvalues, W will give me my eigenvectors, and it's just going to be np.linearalg, linalg.eig, not h, and then I give it my matrix. And then let's just print A. So there's my two eigenvalues, 6 and 1. I already said that. That agrees with what I had. What about my eigenvectors? If I print W, you can see what it is. It gives me 2 vectors, but these are vectors as a column. Okay, so this vector right here is one of the eigenvectors, and this one right here is the other one. So let's print that out. I'm gonna say print W1 equals, and then I'm gonna print. I can take the transpose of that solution and then print the first element. So W dot T takes the transpose, and 0 is the first element, and then I'm gonna print the second one. W2 equals W dot T. 1. So a lot of these commands are like magic spell books, right? You're looking up in the spell book and you're casting fireball or whatever, and so sometimes you don't remember that you need to do .t, so you look in your spell book, right, and then you cast the spell. So in this regard, it's partially magic, and that's fine. Magic is cool. But here's W1, here's W2. So this is the vector that we already did. I'm going to show you that this is indeed a solution. It's a normalized solution. So let's take this, copy that, and go back over here to Web VPython, and I'm going to put this as R1. I'm just going to delete that, copy, and then I'm going to put a comma here. And then I'm going to print R2, let's say, and then I'm going to also print norm or mag R2. So mag tells me the magnitude of that vector. And let's see if it is indeed normalized. So that is the same thing that we had, and then that is has a magnitude of 1, so it did work. Now let's try the other one, which we didn't solve analytically. I'm going to copy this, and let's put that one in. I know it seems kind of silly to go back and forth, and you technically can do VPython in NumPy, but I don't like to because some weird things happen, and I've never had a great experience. And I'm going to put a comma right here. I'm going to run this. There you can see the two vectors. It is a solution, and it has a magnitude of 6. Oh, that's R2. It's 6 times that, right? So I'm sorry. Yeah, I printed R2, which is the output, which is lambda times that. And so if lambda is 6, then the magnitude would be 6. So that is right. Pretty cool. Okay. Now, if you want to do a 3 by 3 matrix, there's no difference, right? The only thing that I would do is up here, I would change this to a 3 by 3 matrix. I'm not going to do that. I just want to introduce you to the 3 ways that we can do the eigenvalue problem manually by rotating around vectors until you find one, using this algebra and matrix algebra, and then using real Python. So there you go. We're going to do some more eigenvalue problems later, but this is your introduction to eigenvalues. I'll talk to you later. And eigenvectors.